Okay, good morning. So this is actually the last formal lecture of this quarter. And so I'd like to finish the discussion about how ADA-CFT works microscopically from the perspective of entanglement. So to discuss that, I need to prepare some more tools. So first concept that I'd like to introduce is the von Neumann entropy. So we discussed the Shannon entropy, which is defined for classical probability distribution. You can think of this as a quantum version of the concept. So suppose you have a Hilbert space. And suppose we have an ensemble of states that state I can be realized with probability Pi for some orthonormal state I. So we regard this as orthonormal. And so then we can define, we can consider associated density matrix. And the von Neumann entropy is defined to be minus of trace of rho log rho. And so in this particular case, it is defined to be the same as the Shannon entropy. Okay, but so in this case, it reduced the Shannon entropy, but we can define this notion of von Neumann entropy in a more general situation. And this concept is in particular very useful in quantifying the notion of quantum entanglement. So when two systems are entangled, it would be useful to quantify how much two systems are entangled with each other. So let me give you some example. So suppose you have a two-dimensional Hilbert space. So let's first consider the simplest possible case. So suppose you have two-state system, and suppose you have a copy of this. So we have two copies of two-state systems. Okay? So suppose we consider just tensor product of a pure state like this. So there's no interesting entanglement. But, for example, there is a state which is sort of maximally entangled in some measure. And this kind of state was considered by Einstein, Podolsky, Rosen when they first come up with the concept of quantum entanglement. And it is given by this. So in some measure, this is a maximally entangled state. And for example, when Bell's inequalities, which was confirmed by experiment and Nobel Prize was awarded a few years ago, deal with this kind of state. So there is actually a way to quantify the degrees of entanglement of this, and one measure is entanglement entropy. My chalk is getting short. I should use this one. So suppose you take any state. Oh, this is not good. So let's see which one is better. suppose I take any state from this tensor product Hilbert space. And so what you do is to define reduced density matrix, which is defined to be partial trace of this state over the Hilbert space B. So this acts on the Hilbert space of A, and then you define the entanglement entropy for this state with respect to a Hilbert space A as minus of trace of HA of rho A, log rho A. And this definition that may not look symmetric in A and B, but it's easy to show that this is actually symmetric in A and B. So that's why I didn't write A to it. You can show that if I use a logarithm of base 2 in this particular case, then you can actually show that this is actually going to be 0 when I choose this state to be not entangled state like this, decoupled state, and it's going to be 1 for psi is EPR pair. And in fact, 1 is in this case the maximum amount of entanglement entropy one can have. So you can say that this has least entanglement, this has the maximum entanglement with respect to the entanglement entropy. We can also show, and this is something I cannot cover for the limited time, but there's a notion defined in quantum information theory called local operation and classical communication, which is basically an operation which preserves the amount of entanglement of quantum system. And using that, one can prove that if you have a particular state, and suppose you take some n tensor product of this, and suppose you take n to be very large, which is to say that you have many copies of the same state, then you can show that by an operation called the local operation and classical communication, by which it means that you are just going to do some unitary operation for each of these Hilbert spaces separately, and you only allow some classical communication between these systems, so it won't change the classical quantum entanglement. Then you can show that this state can be actually transformed into tensor product of EPR pair, but only to the amount of lowest integer of n, which is this n, times this entanglement entropy. Okay? So for example, if psi happen to be EPR pair itself, then of course if we take it to the raised to the power n, it is actually EPR raised to the power n, and in that case entanglement entropy is actually 1. On the other hand, if it doesn't have much entanglement, like in this case, then this can be transformed into some state which contains no EPR pair, because in that case entanglement entropy is 0. So this works for large n. So in some sense, one can think of this entanglement entropy as the amount of the number of EPR pairs in a given system. So how much states are connected to each other by each EPR pair. Okay. So let me do some example of calculation. So we can try to calculate this entanglement entropy in two-dimensional conformal state. And this is done by this famous paper by Calabrese Cardi in 2004. Okay, and so they consider the following system. Suppose you consider two-dimensional CFT with Cauchy surface to be circle, and then there is a time. Okay, so now suppose you separate this Cauchy surface, the circle, into two segments. The region A, which is the line segment here, and its complement. So, so the total Hilbert space of this CFT on this circle can roughly be decomposed into tensor product of Hilbert space of A and A bar, because we are considering a local contact theory. So there is a local degrees of freedom on this side and local degrees of freedom on this side. This actually is a rather naive picture, and there is a more rigorous version of the statement which are studied by many people, especially people working on operator algebra and algebraic contact field theory. But for now, let's take this naive point of view. And if you take naive point of view, then we can do this machine, run this machinery. So for example, suppose you take the vacuum. And then define the entanglement density matrix for region A by taking trace of the vacuum state over the Hilbert space over the concrete. Okay, so this defines the density matrix. And then we can define entanglement entropy. But as an intermediate process, it's useful to actually calculate first this quantity called Renyi entropy, which is defined to be the trace with some extra numerical factor of logarithm. So from now on, I take logarithm with base E of Napier number of trace of this Hilbert space of rho A power to n. Okay, and so this is a useful quantity, and in particular, if I take the limit of n goes to 1 of this Renyi entropy, then it gives you von Neumann entropy. Okay, so what Cardi and the collaborators did is actually to calculate this exactly for any unitary conformality theory. And the beautiful fact is that in this particular setup, the entanglement entropy depends only on the central charge of this CFT. And the argument goes as follows. So, so what this calculation would look like? Well, we are calculating trace of rho A to the n. So what would this look like? Well, so you have this Hilbert space. So let's open up. So suppose we open this up. Suppose this circle is very large. So we have this Cauchy surface. This is, you can think of this as a circle whose radius is very large. And we have this region A bar. And then we have this region A. Okay? And what you do is that you divide the Hilbert space. So continue here. So this is also A. And so what you do is that first you start with a vacuum state, but then you first take the trace over Hilbert space of A bar of the vacuum state. Okay, so and then so you have this. You just take trace over this region, and then define rho A, and then raise it to the power of n, and then trace it over Hilbert space of A. That's how you calculate this, right? So what you are doing is that you first calculate this quantity. You just take trace over this one, and then take multiple of this rho times n times, and then take trace. So this is nothing but the calculation of the partial function on the n-sheeted cover of R2. So namely that what you do is that you cut this here. So this is A bar, and this is A. You open up A side, and you make n copies of this. And then, so you suppose you have n copies of this. You have n copies of this. And then what you do is that you put numbers, 1, 2, and then 2 is identified with this 2, and 3, and 3, 4, etc. And then you have 1 prime, 2 prime, 2 prime, 3 prime, 3 prime, 4 prime, etc. And then basically identify it. So you go around here, come out here, and go around here, come out here, go around here, etc. Okay? So if you do that, you calculate the partial function. Now, how can you calculate this partial function? Well, this actually, in this case, it is actually very easy to do that. And the reason is the following. So if you, in a situation like that, there is actually a nice way to uniformize this surface, which is that to map this, so this n-sheeted cover of R2 is in terms of conformal structure, the same as R2 itself, and there is actually a map to do that. If I consider coordinate Z to be the uniformized, so suppose this point is U and this point is V, and suppose this is the coordinate is W, then we can actually introduce new coordinate Z, which is defined as W minus U over W minus V to the N. Then, right, so let me see this one. Yes. Yeah. So then, sorry, this is one way. I'm sorry. So as W goes to around U, it goes to new sheets, right? This map has n-sheeted covering of W plane, and so if you go to Z space, then it's actually uniformized. So what you do is that then you ask how the energy momentum tensor gets transformed. Well, the energy momentum tensor is 2 tensor, so you might think that it should transform like that. But as we discussed in the first quarter, the winter quarter of the general discussion of conformality theory, there is actually inhomogeneous term in the transformation of energy momentum tensor, and it is like that. So what this means is that if you calculate, suppose for example you are in the coordinate Z, where we just have R2, on which the expectation value of energy momentum tensor is 0. Then expectation value of the energy momentum tensor in this surface is actually given by the Schwarzschild. And if you know how to calculate the expectation value of the energy momentum tensor, then from that you can infer actually the value of the partial function. And that's what you can do. Now, the Schwarzschild, we defined the Schwarzschild in the last quarter, but let me just remind you that it is given by this. So if you have this map, then we can actually calculate this. And then from that, we can actually calculate the value. Okay, so this is the calculation of the Rayleigh entropy, and this was done by Hardy and Calabrese in that paper. And so once we know we can map that to the R2, we can use the fact that energy momentum tensor vanishes there. So then we can calculate the energy momentum tensor of the original n-sheeted cover space. And from that, we can actually deduce that this is equal to some constant times u minus v to the minus c over 6 n minus 1 over n. And this constant can depend on n, but is independent of u and v. So from that, we can calculate the ready entropy to be equal to c over 6 of n, 1 plus 1 over n of log of L plus constant, where L is the distance between the two cuts. And then from that, we can calculate the entanglement entropy. Therefore, Neumann entropy to be log L. Well, so plus constant. As I said, this decomposition is a little bit subtle, and because of that, this entanglement entropy is actually ultraviolet divergent quantity. So we may need to introduce, it may be useful to introduce some ultraviolet cutoff. And so that this quantity L, which has dimension of length, can go into the logarithm. Okay, so this is the calculation. So this calculation was known, and then right after this calculation was done, there was actually interesting observation by Ryu and Takayanagi, who proposed the ADS CFT version of the same calculation. So this calculation is valid for any two-dimensional conformality theory. But then you can ask, well, how is there a corresponding calculation in gravitational theory in ADS if the CFT has gravitational dual? And this is what they proposed. So Ryu-Takayanagi formula in ADS CFT. So here is what they propose. So suppose you have, for simplicity, suppose you have any two-dimensional any CFT, any dimensional CFT, and which has gravitational dual. And let's choose a Cauchy surface. So boundary is S. So suppose you have CFT D and ADS D plus 1. And so the boundary is SD minus 1. And then you have this Cauchy surface, which is a D-dimensional disk or hyperbolic space. Okay? So what they propose is that if there is a region domain in D-1 dimensional circle, which we call A, then they suggested, well, we should consider some minimum surface go into the ADS, subtending the boundary of A, namely that ending on the boundary of A. And so let's call that R, or maybe A tilde in this case, so A tilde. So let me blow it up. So this is a boundary. So this is SD minus 1. And then suppose you have a region A. Then they suggest, well, you choose A tilde with the property that the boundary of A is the same as boundary of A tilde, and A is actually homologous to A. So by this I mean that there is actually a region M. So this is to say that there is a region M whose boundary is A minus A tilde. And A tilde is a minimum surface, minimum area. And then what they proposed is that the entanglement entropy for the state that we are considering in ADS CFT with taken partial trace in the complement of A is given by the area of A tilde normalized by 1 over 4 times G Newton. Okay? So evidently they were inspired by the famous Bekenstein-Hawking entropy formula, which you have similar formula, except that in that case area is area of event horizon of the black hole. So here they are considering this area to be the minimum surface subtending A. The immediate check is that if this boundary CFT is two-dimensional, then the Ryu-Takayanagi formula reproduces Cardi and Calabrese formula. Okay. So this is a simple calculation one can do, and they actually check this calculation. So this leads to a variety of interesting insight into the property of ADS CFT correspondence now. One of the interesting observations is that this is closely related to the entanglement wedge discussion that we had at the last lecture. Namely, that the question of how much information that the boundary domain have for given regions. So remember that there was a notion of entanglement wedge. So suppose you have this region, and suppose there is a boundary region A. So then you can consider some region inside of A tilde, inside of this ADS, and call that as A tilde, and there is this shaded region. And so let's call that as, we call that as M, I guess, so let's call that as M. Okay? And the entanglement wedge is defined to be the domain of dependence of this region M sandwiched between A and A tilde. Okay, and so for variety of observation, and in particular the calculation of the bulk reconstruction formula that we discussed last lecture, it has been proposed. The proposal has been that this density matrix calculated by this is dual to the entanglement wedge. Of A. So namely that the classical gravity calculation that you can do, classical gravitational information that you can extract from this particular density of state are all encoded in the domain of dependence of M and vice versa. So this was sort of a proposal that was put forward based on this bulk reconstruction calculation. But this leads to the puzzle, like the puzzle that I mentioned in the last lecture. So let's revisit this puzzle in view of this interpretation of this region in terms of entanglement. So remember that there are two puzzles. about this entanglement wedge reconstruction. One was that suppose you have this region, point over here, and suppose you choose two regions. One is this A over here, and the other is this B over here. Then you can see that the Ryu-Takayanagi surface subtending this A includes this point. But Ryu-Takayanagi surface subtending B also includes this point. So this suggests that this local excitation of this point can be described both in terms of region A and region B. So how is it possible that the same state have two different presentations? The other puzzle was that suppose you have some local excitation in the middle, and suppose you divide the boundary into, say, 3 segments, A, B, C. But then you can have a situation where none of the entanglement wedge for none of these regions covers this local excitation in the middle. So that means that even though one may think that any operator on the boundary can be expressed in terms of this local operator in region A, B, and C, but region A, B, C individually cannot describe this local excitation here. So how come it is possible? So this was a puzzle raised around the time when this entanglement wedge reconstruction was proposed. And this was actually rather conclusively addressed by the work by Almheri, Don, and Harrow, and also Harrow by himself. So let me review their resolution to this puzzle. So there is this resolution. So there was a puzzle, and then there is a resolution. So this was by Almheri. Shidon and Daniel Harrow. So this is 14.11.7041. And then there is actually a very nice paper by Harrow, Don, Harrow, and Wall, 1601. 05410, and then a nice summary of all of these, including many review of basic concept in this paper. So if you are going to read one paper on this, then this is the one that I would recommend. But so what they showed is that this kind of geometric reconstruction of the bulk excitation in terms of boundary degrees of freedom is exactly that of quantum error correcting code. And then from that perspective, there is no puzzle like that. But what one needed to do was to have proper interpretation of what the bulk excitation would mean. So there is a notion of quantum error correction. So let me describe that in some example. This is not a class of quantum information theory, so it's within the next 30 minutes or so, it's too much to cover. So let me just give you some basic idea based on some simple example. Okay? So in the classical computer, you can do error correction by making copies of the same classical data set. But in quantum computation, you can't do that because there is actually a famous theorem by Zurek that it's called quantum no-Xerox principle, that there is no unitary process to transform the given state in some Hilbert space into copies of the same state in tensor product or Hilbert space of the tensor product of the same Hilbert space, copies of the same Hilbert space. But there is something else one can do, which is the following. So suppose you have 3 copies of the same Hilbert space. So 0, 1, 2. So this is the Hilbert space A. And then there is a Hilbert space B, same set of basis vector. And then there is a Hilbert space C with the same set of basis vector. Okay? So these are 3 copies of the same Hilbert space. And define entangled state of these 3 Hilbert spaces in a particular way. So 0 children is defined to be, this is just like EPR pair, but that was 3 copies. And then 1 children to be equal to 1 over square root of 3. 1, 2, plus 1, 2, 0, plus 2, 0, 1. And 2 children is equal to 0, 2, 1, and 1, 0, 2, plus 2, 1, 0. Okay, so the original this Hilbert space is 3-dimensional, so you have 3 copies, so you have 27-dimensional Hilbert space. And in this Hilbert space, what you do is that you choose 3-dimensional subspace, but cut diagonally across tensor product of these 3 Hilbert spaces, and this is called chord subspace. Okay, so if you look at the quantum information literature, they often draw this kind of diagram, so where you have this transformation, and there is a chord subspace, and then there are physical subspaces. And so in this case, the chord subspace is this 3-dimensional space. And then physical subspaces are A, B, C. So on this side, you have 27-dimensional space, the 3 to the 3-dimensional Hilbert space. Here you have 3-dimensional space, and this map is defined in this way. So now, in this chord subspace, here is what one can do. So suppose you have any unitary operator, U1, 2, acting on tensor product of A and B, such that if you tensor this 3, then it actually maps to the first state with some prescribed state of the other 2. Okay, so you can easily define such unitary map. So this is the definition of unitary map. Excuse me. Now, so if we have such unitary map, then you can show that for any operator which maps I to linear combination of the 3 states in the Hilbert space A, O12, which is defined to be U12, dagger O U12, acts only on A tensor B, and trivially on C, such that O12 acting on I children is equal to Mij J children. Namely, that you can this operator O12 defined in this way mimics what this original operator does in the original Hilbert space. Okay? So this acts on the code subspace just like the original Hilbert space would act. So you can say that you have encoded successfully this operation defined on the original Hilbert space in this code subspace. And the reason that this is good is that this is actually better protected. You can actually use this unitary operator to correct error. So suppose you start with this Hilbert space, and then suppose you make error in the Hilbert space C. Then you can actually repair this error by using this unitary operator. Okay. So this is sort of how this quantum error correcting code works. And in particular, anything you do on the single Hilbert space can be mimicked in this code subspace. Okay, so now one can ask, well, what it has to do with the program? Well, actually, so the claim is that this is exactly what holography, how the holography works. So here is sort of interpretation, holographic interpretation of what is happening here. So the idea of, in this quantum entanglement business, so suppose, for example, you consider this full physical Hilbert space. So let me draw this. So the analogy here is that you have this physical space, and you think of this as CFT Hilbert space. And so these are physical subspace, so you have A, B, C. And this is as if you divide the CFT Hilbert space into 3 segments. Okay, so this is a picture one should have on the right side. And then you have on this side, you have gravitational excitation. In ADS. So you have this cold subspace. And here you have the CFT Hilbert space. So what is happening is essentially using this map, you can identify this cold subspace as a subspace of this CFT Hilbert space. And this is where the perturbative excitation of gravitational system in ADS reside. And so then what one can see is that suppose you have this conformal Hilbert space, and the region is divided to A and A complement, then CFT Hilbert space can be divided into A and its complement. And the cold subspace can also be decomposed into M and M complement, where M means this region, and M complement is this region. And then what you can do is that any operation you can do over M can be mimicked by appropriate operation in M, in H of A, if M is in the entanglement wedge region of A. And this way there is no contradiction. So for example, here, so the first puzzle was that why is it that the same local excitation has two alternative descriptions in terms of A and B? And you can see that in fact for each pair, in this case 1, 2, 2, 3, 3, 1, you have different operator acting on 27-dimensional Hilbert space, but they have the same action on the code subspace. Okay, so this is sort of how it works. And in this paper, they give more detailed discussion on the way that this works. Okay, so this gave a very sort of deep insight into how a holography works in microscopic fashion. And this led to some variety of new insight into the gravitational system in ADS-CFT. So let me tell you a few observations one gained by understanding this Ryu-Takayanagi formula and the entanglement wedge reconstruction that we have seen. So one thing that I would like to first mention is that there are a variety of expectations about gravitational systems that that people have speculated, and so one idea that people had about gravity is that the gravitational system should not have any global symmetry. So it has been long argued that if you have quantum gravity, then you cannot define the notion of global symmetry. And this was actually first proposed by John Wheeler around 1957. There is actually a nice article in Annals of Physics that Wheeler co-authored with Missner, where this was clearly stated. So by this I mean the following. So as I have mentioned a couple of times already in this lecture, in quantum systems there are two notions of symmetry. One is global symmetry, for which you have nether charge, and it acts non-trivially on the Hilbert space. And there's a gauge symmetry, which is used to sort of describe a physical system in terms of gauge degrees of freedom. But those symmetry don't act on the Hilbert space. Here we are considering the symmetry that acts non-trivially on the physical subspace. The original argument makes use of existence of black hole. So basically, suppose you have a black hole, then if you have a gravitational system which contains black hole, then if you gather sufficient energy and mass in some localized region, that local excitation might collapse into black hole. And if it happens, you can lose the information about global charge. So the reason is that if you have gauge symmetry, then there's a gauge field which sort of communicates a gauge charge to outside. So for example, if you have a black hole with positive electric charge, well, you can measure the amount of charge by measuring electromagnetic field outside of the black hole. But if you have global symmetry, there are no gauge fields that sort of convey the information about the charge. And so suppose you form black hole with some conserved charge, but suppose it is global charge. Then you can show by simple argument that the amount of the Hawking radiation carrying positive charge, carrying away positive charge from black hole, is the same as the amount of Hawking radiation carrying negative charge by the charge symmetry. So that means that as black hole shrinks by Hawking radiation, that it shrinks but preserving the amount of global symmetry charge in the black hole. And suppose the black hole evaporates away. Well, the information about the global symmetry is now gone. So that seems to be the process in which global symmetry is violated. Okay, so this is a hand-waving argument, and there are some loopholes in this argument. But if you use the ADS-CFT, and in particular this type of idea about interpretation of holographic reconstruction in terms of quantum error correcting code, then you can actually prove the absence of global symmetry in the case of ADS-CFT. So in fact, this is my paper with Daniel Harrow. So let me briefly describe what we did. this is my last lecture for this course, so I'm allowed to, I hope, briefly tell you about my own work too. And so, like I said, the basic idea of holography is that it's very much like quantum error correcting code. So there is a CFT local state. Which corresponds to what's called the physical qubit. And then there is an ADS local state, which corresponds to what's called logical qubit, or code subspace. So basically, you encode the information that you want to process in the quantum computation, distributed around physical qubit to protect the information. Okay, and so how do you prove that global symmetry does not exist? Well, so here is the idea. So suppose you have ADS CFT. So on the boundary you have CFT. And in the bulk you have ADS. So suppose there's a global symmetry. So in that case, where there's a group G, by Wigner's theorem, well, at least in the standard group, nowadays there's a more generalized notion of symmetry. But let me consider the traditional type of symmetry for which Wigner's theorem applies. In that case, for given symmetries, there is a set of unitary transformation, and they make a group by multiplication. So there is a group associated to symmetry, and for each element of G, then there is a unitary operator acting on the Hilbert space. Now, if you have a continuous symmetry, there is a Noether theorem. So there is a notion of Noether theorem. So Noether theorem deals with continuous symmetry. So there is actually a discrete version of this I can briefly mention. But suppose there is a symmetry G which is continuous. So in that case, you can consider infinitesimal version of this. So, or more generally, any element of G can be written as the exponential of I times some epsilon A HA, where HA is a Hermitian operator. And if this is acting on the local quantum field theory, then there is actually a conserved charge, conserved current, J, A, depends on X. And so HA is given by integral of D minus one dimensional, so in this case a Cauchy surface of J. Well, if you use form notation star of J of A. So basically it's an integral of the Cauchy surface. So in particular, what this means is that suppose you divide the sphere into some segment, A1, A2, A3, A4, A5, in such a way that SD minus 1 is a union of AI. Then, well, so this is HA is like that, so that means that the HA is summation of I of integral of star of A over J. And since G is exponential of H, so the unitary operator corresponding to this G, we should be able to write it as product of unitary operator acting on each of these regions. where this region, each of these AI is an exponential of I of epsilon A of integral of star of J A of AI. So one should be able to write. So if the boundary is divided into region, then there is actually associated unitary operator for each of these regions. And this implements the symmetry operation. So this is what Noether theorem says. Okay. This notion that if you divide the Cauchy surface into segment, then the symmetry implementing unitary operator can be expressed as product of operator acting on each region is actually more general than what originally the Noether theorem intended. There is actually a beautiful paper in the algebraic quantum field theory by Buchholz and collaborators. Where they show that this actually also works under relatively weak assumption for discrete symmetry as well. So suppose for here we consider the continuous symmetry like SU2, SU3 or E8, etc. But you can also consider some discrete symmetry like Z2 or the Mashu group or the monster or whatever discrete group. That it has been shown that this also holds.
Does this hold for like anti-unitary symmetries?
Well, that's a very interesting question. I think so. Yeah. In fact, I think so. That's a very interesting question. In fact, anti-unitary symmetry typically involves time reflection.
Yeah.
So here I'm considering global internal symmetry. So space-time symmetries should be discussed separately. But so let me stick to the internal symmetry. So for internal symmetry, whether it's discrete or continuous, this is true. Now, if this is true, then we can go back here and ask what happens to this local symmetry, the global symmetry in the context of ADS-CFT. Well, so suppose there's a global symmetry in gravitational theory in ADS. Then there ought to be some local excitation in ADS which carries charges. Otherwise, it does not make sense to consider this as a symmetry. So for example, one should be able to consider some local excitation in the middle of ADS, which carries some non-trivial charge. So that means that if you define this unitary operator that implement global symmetry, it should have non-trivial commutation relation with this local excitation. But that's problematic because suppose I divide the boundary segment into pieces. And then you consider some regions. Then what I have just mentioned is that for any group element, the symmetry implementing operator U of G can be decomposed into product of operator acting on each of these regions separately. And on each of region, there is a entanglement wedge associated to it. And if you divide the boundary segment small enough, then none of that touches this point. So that means that obviously by this ADS-CFT construction, that this symmetry implementing data operator commutes with this local excitation. So this is a contradiction. So it's contradiction because we assume that there is actually a global symmetry in ADS for which there is a charge state. And so that assumption is false, and that therefore proves the absence of global symmetry by contradiction. If you go back to look at what was the issue with this, one can see that the issue was that exactly because of the way that the data charge acts, the data theorem works, that the symmetry implementing operator is a product of local unitary operator. It means is that according to this quantum error correcting code property, that it acts transversely on the physical qubit, that it acts like tensor product of physical qubit. And any operator that acts like an exact copy of tensor product of the same operator acts trivially on this quantum error correcting code. So cannot act on the code subspace non-trivially. In order to act non-trivially on the code subspace, this operation has to generate a non-trivial entanglement between them, or changes the entanglement between the physical qubit. And this doesn't do it because it's just a tensor product. So this is sort of deeper understanding of how this works. Okay. So by using this ADS-CFT correspondence, one can prove this type of interesting theorem about ADS-CFT or gravitational system in ADS in general, using relatively simple argument. Let me give you another example. So I showed you that there is no global symmetry in ADS, gravitational theory, and there is no global symmetry in gravitational system. And in particular, we were able to prove that the statement in ADS-CFT. I can also prove another thing that does not exist, which is that there is no adjustable parameter in quantum gravity. So if you write down some, if you consider some gravitational system in ADS, and you can write down any sort of low energy Lagrangian, then you might think, well, we can cook up some system which can parameters. And parameter can be adjusting the mass of some the charged particle in the system, or mass can be adjusting some interaction between them, etc. So you can have many parameters in a gravitational system. But one can show that if ADS-CFT correspondence works, and if you have a gravitational system in ADS that obeys ADS-CFT correspondence, then if that theory, gravitational theory, has any parameter, then it's not a pure parameter. It has to be it means that if you have such a parameter, it means that there must be some massless scalar field, and the parameter is not adjustable parameter, it's actually an expectation value of that scalar field. So you can actually prove that statement. So let me prove that statement. So this is actually proven in ADS-CFT correspondence. So this actually, I gave the proof in my summary talk at the SLIM conference in 2022. And I'm actually writing up some argument with my collaborator now. But let me just give you the argument. So suppose you have a gravitational system. And suppose lambda is a parameter. So that means that you have some local Lagrangian in gravitational system in ADS with some parameter. Right? And then you can change it. You can change lambda to lambda plus delta lambda, etc. You can do this without any cost. So suppose you can do that. Well, ADS-CFT correspondence means that there must be some conformal field theory on the boundary with the same parameter. So if you can change the parameter in gravitational system, you should also be able to change the corresponding parameter in conformal field theory. Okay? But actually, we know a bit more about how the change of parameter in conformal field theory should look like. It is actually known that every continuous deformation of the parameter should be described in terms of exactly marginal operator. So in CFT. So by this I mean that suppose CFT is in D-dimensional, then exactly imaginary operator O has a physical dimension, the mass dimension D, and transforms as a primary operator. Primary local operator. And 3-point function vanishes, etc. So it satisfies a bunch of properties such that the this CFT Lagrangian can be deformed as this. The addition of this operator. Okay. So this is known. But therefore, whenever one have this adjustable parameter, one has to have exactly imaginary operator. And it has to be a primary field in conformal field theory. But I have told you in the last couple of lectures when we discussed the dictionary in ADS CFT correspondence, that for each primary operator in conformal field theory by operator correspondence, there is a state in conformal field theory, and for each state in conformal field theory, there must be a state in gravitational theory. And in the case of primary operator, the corresponding state in gravitational theory, if the gravitational theory is weakly coupled, must correspond to some particle state in gravitational system, and in particular O, which is the exactly imaginary operator. In CFT correspond to phi, which is a massless scalar particle. In ADS with flat potential. Such that the variation of lambda corresponds to expectation value of phi. So this actually shows that you cannot just have parameter in gravitational theory. Whenever you have parameter that is adjustable, there must be some massless scalar field whose expectation value gives you that parameter. So in particular, that means that the parameter is not just rigid parameter, it can be varied locally. So we have seen the two statements, absence of X, where here you have absence of global symmetry, and here you have absence of no parameter. And in fact, these two statements are related. So there is now a notion of P-form symmetry. Which is a generalization of the traditional notion of symmetry. This was actually introduced by Anton Kapustin and collaborator. And the traditional symmetry is called P equals 0, the zero form symmetry. So in that case, there is for each Cauchy surface, there is a charged operator, there is a symmetry implementing operator, and the charged operators are sort of local operators acting on the Hilbert space. But there is a generalized notion of this. For example, when you have P equal 1, then the charged operators are lines, the one-dimensional extended object like Wilson lines. So there is also the minus one form symmetry, for which the charged operator corresponds to this primary the parameters. So P equal, if existence of P equal 1 symmetry corresponds to the parameter. In theory. So in particular, so therefore one can say that the absent no global symmetry that I mentioned over there corresponds to the case when P equals 0. And the no parameter that I discussed here corresponds to P equals minus 1. So you can see that this type of notion can be sort of combined into a single picture. So that's pretty interesting. I only have perhaps 10 more minutes. So let me mention one more small observation that one can make about this ADS-CFT correspondence and the Ryu-Takayanagi formula. So this is about some entropy inequality. So let me see if I have notes on this subject. Okay. So before we go on, let me mention a couple of things. Okay, so suppose we have two sets of events. So let me so to go forward, let me introduce the notion of mutual information. Okay, so suppose you have two sets of events, A1 to AN and B1 to BM. Okay, so then we can calculate a joint probability of AI Bj, for example. So namely the probability that A happens and at the same time B happens. Then of course you can consider conditional probability. So for example, the probability of Bj happens condition that A has happened, which is just given by this ratio. Right? So there is this notion of conditional probability. So obviously, if you have a conditional probability, then you have conditional entropy. Which is given by S of AI or BI, which is given by, so this is a standard Shannon entropy, but with this condition that AI has happened. Okay? Now, obviously, the conditional entropy is not symmetric under exchange of AI and BI. But there is a notion of mutual information, which is closely related to this conditional entropy, but is symmetric, and it is given by the following formula. It is actually a Shannon entropy for B happening minus the Shannon entropy of B conditioned by A. But you can show that it's in fact by simple algebra that this quantity is given by this. So obviously this is symmetric. Now, this mutual information has a nice interpretation, which is that it's a question, it's a information, it's a quantity about how much uncertainty about B is reduced by knowing that A has happened. Right? Okay. So this mutual information, definition of mutual information suggests that there must be lots of interesting inequalities, involving von Neumann entropy and Shannon entropy. Because, for example, one would expect that one should gain information by knowing B has happened. So that means that the mutual information has to be positive. So that means that the mutual information A, B should be positive, namely that SA plus SB minus SAB has to be non-negative. And so this condition is actually called sub-additivity. And you can actually prove this for any Shannon entropy or von Neumann entropy. There's actually a more subtle notion of sub-additivity, which is SAB plus SBC minus SB minus SABC is greater than or equal to 0, and this is called strong sub-additivity. Okay, this is more non-trivial to prove, and obviously you can see that if the region B is trivial, then it's reduced to the ordinary sub-additivity. So, for example, proving this for Neumann entropy is actually non-trivial, but it is true for any von Neumann entropy. And this type of inequality has played a very important role in this series. Now, as I said, this actually is rather difficult to prove in von Neumann entropy, but from the Ryu-Takayanagi formula, it's actually very simple to prove. So suppose you have a holographic system. The Ryu-Takayanagi formula says that if you have a region A, then the Ryu-Takayanagi formula can be given by minimum surface subtending A. And suppose you have a region C which may overlap with A, then Ryu-Takayanagi surface gives you the von Neumann entropy for A. Now, if this overlapping region is B, then Ryu-Takayanagi surface is given by this. And for the union of ABC, then it is given by this. Right? So you have this four construction of entropy. This is A union B. This is A union C. This is B, and this is A union B union C. Okay. So you can ask, well, so how do you see this inequality? Well, it's very easy to see that because this is homologous to this, and this is homologous to this. Okay. So you can ask which one is bigger, which has more area. Is this longer than this one? Certainly yes, right? And is this longer than this? Certainly yes. And there's a reason for this. The reason is that this is longer than this because these two surfaces are constrained in such a way that they meet here. On the other hand, this surface and this surface separately has no constraint. So it's clear that you get generally smaller minimum surface by removing constraints. So by removing the constraint that they meet here, you can have shorter region. So what you can see is that if it's a soft bubble, if you cut this, it's going to shrink down there and up there. So, but then that statement just proves this inequality. So you can see that this geometric construction give you automatically this type of inequality. The inequality satisfied by Ryu-Takayanagi formula has been extensively studied. There is actually my paper with Imbao and collaborator on that subject also. But there is also inequality that is particular about holographic construction. So, for example, there is an inequality called monogamy of mutual information, which is to say that IA of BC minus IA B minus IAC has to be non-negative. Okay. This is called monogamy because there's a moral to this inequality, which is to say that if A and B has some mutual information, then that cannot be shared effectively with a third party. So if you have three parties, and if A and B know some information, then you cannot share that amount of information with another party C without compromising the information that these two parties hold. So this is called the monogamy of mutual information. Now, this inequality has been proven for Ryu-Takayanagi surface, but not true for general von Neumann entropy. So Ryu-Takayanagi surface, this monogamy of mutual information can be as easily proven as in this case. It's just a geometric property of minimum surface. But for Neumann entropy, there are counterexamples. So for example, if you consider what's called the GHZ state, which is analogous to this EPR pairs, but extended to 4 parties, then that actually one can show that this combination of mutual information is actually negative for that combination. So for Neumann entropy, it's not true. So this is interesting that this monogamy of mutual information is particular to holographic systems. So one might think that therefore it actually characterizes the existence of holographic duo. For the last few years, actually for about the last 5 or 6 years, this monogamy of mutual information plays a very important role in black hole physics. So for example, the question about the black hole information paradox and some puzzle associated to black holes such as firewall paradox are closely related to the existence of this monogamy of mutual information inequality in gravitational systems. That there are several interesting lectures one can see. More generally, for many more parties, you can ask, well, what is the situation of this type of entanglement inequalities? It is actually known and proven that for Shannon entropy, there are actually infinitely many linearly independent entanglement inequalities. For von Neumann entropies, it's not known whether so if you increase the number of parties, whether the number of linearly independent entanglement inequality grows indefinitely or not is not known. But there are some numerical calculations which seems to suggest that there are also infinitely many von Neumann entropies. It has been proven that for holographic entropies, for each number of parties, the number of entanglement inequalities is finite. And in fact, it makes a cone. So this was actually proven in my paper with Nimbao and collaborators. So there are lots of interesting characteristics of holographic system that one can actually derive using this type of code. Okay, so this is the last. This was the last lecture in this course. There will be 2 more presentation sessions coming up, and I look forward to that. But the message I would like to give at the end of this course is that well, string theory gives you a very concrete and explicit construction of consistent theory of quantum gravity that we can learn a lot from this. And one thing we have seen is that for gravitational system, the quantum properties are very different from quantum field theory. That there are things about gravitational systems that seems to be rather different from ordinary quantum field theory. And so understanding this, I think is very important. And string theory gives you a very concrete example of what's possible and what's not possible.